All right, so welcome back. This is a pretty straightforward question in the sense that it's just asking you to figure out, is this a redox reaction? I'll talk a little bit more. I have a question in the chat there. I'll talk a little bit more about your final after, but the final exam schedule should be posted for you guys. If it's not posted, I'd be very surprised. But anyways, your chemistry 1120 final, I'm pretty sure, is Saturday for some reason, December 5th at 1 p.m. So Saturday, December 5th at 1 p.m. Your exam calendar or schedule will be posted soon if it's not already, not by me, but by the college. They typically send an email or post it on their website. And I'll be making updates on my D2L as well. But from my memory, I haven't looked at it today, but from yesterday, it's Saturday at 1 p.m. I've never had an exam on a Saturday before, but anyways, they've been doing Saturday exams for the last few years. So that's when your final exam is, Abdullah. Okay, so let's do this question. Is this a redox reaction? So there's one step here, basically. We just need to find the charges on all of these elements. The oxidation states would be the fancy term. And if we notice that the charges or oxidation states change, then it's a redox reaction. If they do not change, it is not a redox reaction. And just remember, redox reactions basically, the word is a combination of the word reduction and oxidation, which you'll learn a lot more about in chemistry 2. But it represents a transfer of electrons, which is how we get electricity. So this is something you'll deal with in great detail in Chemistry 1121. Anyways, so this question. Well, first things first, all elements have no charge. So these are not compounds. These are just straight elements. Their oxidation number or their charges are 0. There is no charge on an element. For a compound, however, there are oxidation states or charges. You might be called formal charges, oxidation states. It all means the same thing. So, oops, sorry, I didn't mean to do that. In order to find the charges on this chemical, the ammonia, sorry, we need to do a little bit of work. Okay, not as easy as the other ones. So yesterday, I mentioned that there were 4 rules to follow about oxidation numbers or charges. Rule number 1, if it's ionic, split it into ions. This is definitely not ionic. This is a molecule. Rule number 2 was, take this equation, take this chemical formula and create some sort of math equation about this so we can figure out the charges. What I mean is, I know that 1 nitrogen plus 3 hydrogens would equal 0. This, again, this whole compound is neutral. So that means that the charge I find on nitrogen and the charge I find on hydrogen have to add to equal 0. Okay, so let's go on to rule number 3. Rule number 3 said that if you have hydrogen in your molecule, hydrogen is +1. So this hydrogen here, I'm going to change that to +1. So nitrogen plus 3 times +1 equals 0. Nitrogen, whoops, equals -3. Okay, so I have all of my charges. My nitrogen is -3, my hydrogen is +1, or in chemistry, you might write it as 3 negative. It doesn't really matter how we write it here. All I'm really looking for is, did my charges change? And yes, they did. So the question, is this a redox reaction? Yes, it is redox because the charges or oxidation states have changed. All right, so there you go. That's it. That's redox reactions. You will definitely look at this a little bit more in chemistry 1121. So my mechanical students, if you're a mechanical engineering student, you won't do it. But some of my medical science students, certainly my chemical engineering students, you will look at this in more detail in chemistry too. We'll do a whole unit on this. All right. So that's it for the redox part. I wanted to finish that yesterday, but I just had that one example to do. So today, all I want to do with you guys today is this very important concept called the mole ratio. We won't have too much to do today because the other class I didn't get very far with them. They were a little bit behind, so I had to catch up. But we're almost done chapter 5. We should be able to finish this in Monday's class. Very important topic, however. The mole ratio is a concept, a conversion factor that we use in chemistry to help us with chemical reactions. You can think of it like the recipe of a chemical reaction. So when you make a recipe at home, and baking is a very good example because baking have such strict recipes. Your recipe includes ingredients and then a product, so reactants and product. So if I asked you guys to make me a dozen or 2 dozen, 24 cookies or 24 cupcakes, you would follow the recipe. But when you notice online, when you're looking at recipes, you might notice that they have a certain product. They might only make 12 cupcakes. So you would have to double the recipe. Or maybe you only wanted to make 6 cupcakes. Well, you would half the recipe. And chemistry has a way to do that using mole ratios. Unfortunately, in chemistry, we don't have nice numbers all the time. So like we won't double a chemical equation or triple it. Often we're using very weird numbers like decimals, but it's a very easy process. So a mole ratio is related to a balanced chemical equation. Balanced chemical equations tell us the recipe of reaction, and that can tell us, for example, how much chemicals you need to make something happen, or how much chemicals you can make from the ingredients you have in the lab. It's pretty cool, pretty easy, but very important. There's a bit of a weird example there. How many tires would you need to make 3 vehicles? So, if you were going to write this as a chemical equation, you know that a vehicle, a car, a SUV, a truck, whatever, they all have 4 tires. I'm not talking about bicycles or motorcycles. So 4 tires is in one vehicle. Oops. So if I wanted to make 3 vehicles, how many tires would I need? Well, I multiplied the products by 3, so I'm going to multiply the reactants by 3, and I would need 12 tires. This is a bit of a weird example, but it does kind of explain how balanced chemical reactions can tell you the ratios, the amounts of chemicals you need. So here's the formula. Now, I have a disclaimer. This is not a formula in your data booklet. It's not on your formula sheet. It's not really a formula like moles or mass over molar mass, or concentration is moles per volume or moles over volume. This is a conversion factor. This is really no different than converting from milliliters to liters or kilometers to meters. It's just a conversion factor. And it depends on the equation, the chemical equation you have. So I'm going to show you a bunch of examples of this. Then we're going to apply it to maybe a more real life situation. And then halas, we are finished. So the mole ratio. Now, okay, let me look at this, or let me kind of simplify this equation. There's a lot going on here. There's B's and A's and all this stuff. The way the mole ratio works is within your chemical equation, you are going to convert between 2 chemicals. The chemicals are listed here as A or B. really the good way to think about this is the chemical on top is the chemical you want, or the chemical that's required in the question. So the chemical, this coefficient, and again, you'll see me do this. This is a lot easier than it looks or sounds. But the chemical on the top, the mole coefficient on the top is whatever chemical you're looking for. On the bottom, it's the chemical you are given. So we would call this the chemical that you have, or more specifically, the chemical you are given in the question. So again, I think I have like 4 examples of this. So we will practice this and hopefully it makes sense. It is a lot easier than it looks. Example, how many moles of silver chloride are produced if you have 2.5 moles of magnesium chloride? Now you'll notice that this chemical reaction is balanced. It has to be balanced for this to work. And let's kind of make a little plan here. So I'm looking for this, and I'm given this chemical. So I'll take my pen, I'll write it down. This is the chemical that I'm given, right? I'm given a number here, and this is the chemical that I'm required to find out. Like it's asking about silver chloride. Okay, this is pretty easy. So what I do, I'm trying to find my moles of MgCl2. So I'm going to take the number I'm given, 2.50 moles of MgCl2, and I'm going to multiply it by my mole ratio. The mole ratio is taken from a balanced chemical equation. So I'm going to multiply it by the chemical I'm looking for. Here I have a 2. So 2 moles of AgCl, and I'm going to multiply it by what I'm given, 1 mole. If there's no number in front, it's a 1 of MgCl2. And that's it. I'm multiplying this by 2. So my answer is 5, keeping my significant figures, 5 moles of AgCl. Now, if you're a physicsy person, you know, you're used to doing this in physics, you'll notice that the units cancel. My moles of MgCl cancel, and I'm left with AgCl, silver chloride. Okay, if that still doesn't make sense, I'm going to do some more. Don't worry, I have another couple of examples to do. All right, so let's look at 2 more. You can see the writing down there. Sometimes I like to write it myself. It makes my life a little easier. All right, so we got a question in the chat saying it doesn't make sense, which is totally understandable. Let's look at some more. Okay. How many moles of iron? Oh, I did the same thing this morning, of fluorine, not iron. Wow, my brain. It's been a long semester, hasn't it? So how many moles of fluorine are needed to make 8.5 moles of lithium fluoride? So this is what I'm looking for. This is the chemical that I'm required to find. This chemical is the chemical I have. I know I have 0.85 moles of this, so this would be the number that you're given. Okay, so all I do, I'm going to switch to a different color here. Let's go green. I want to find my moles of fluorine. My brain just really wants to say iron for some reason. I want to find the moles of fluorine. So I take the number that I'm given in the question. The question tells me I have 8.5 moles of lithium fluoride, and I multiply that by my mole ratio. So I use my balanced chemical equation. I put the number that I'm looking for on top. So 1 mole of F2 divided by 2 moles of LiF, and that's it. Done. So LiF cancels, and I'll get my answer. So this, with proper significant figures, my calculator would tell me that my answer is 0.425. We would obviously round that to be 0.43 moles of F2. like, again, think about this like a recipe. My recipe is saying I have 2 moles, like, again, I'm looking at my chemical reaction here. So look at the chemical reaction. I have 2 moles of lithium reacting with 1 mole of iron, and that will create 2 moles of lithium fluoride. That's my recipe. Now, like I mentioned, in chemistry, unfortunately, we don't deal with pretty numbers all the time. So I'm not trying to double this recipe or half it. I'm actually using a recipe that has 0.85 moles. I know for every 1 mole of fluorine, there would be 2 moles of lithium fluoride created. It's a ratio, a mole ratio, 1 to 2. So I take my 0.85 moles of lithium fluoride, I multiply it by my mole ratio. It's always the chemical you're looking for on top and the chemical you're trying to get rid of on the bottom. So it's what you want over what you have, or what's required in the question over the information you are given. And I get my answer. Okay, so why don't I give, now again, this is tough, but there's always some practice worksheets you can do. Why don't you guys try this yourself? Now, you'll notice the red text here. I think initially I would have gotten you to balance this equation, but the answers are already there, so we don't have to worry about that. But just a little hint here. Always, always, always balance your equations, always. Sometimes they'll be balanced for you. Sometimes you'll have to balance them on your own. And we will let you know on the final if you have to balance it. Like, there's really no surprises or tricks. So I'm going to give you guys 2 minutes or so. This shouldn't take very long, but I would love for you guys to try this question. And I will be back in 2 minutes. So around 3:56, 3:57 or so, we'll look at these answers. Okay, so I'll be back in 2 minutes. Good luck. If you have any questions, let me know in the chat. Okay, so I'm recording again. There's a lot of good, well, every answer in the chat has been correct so far. We're getting 3. Let's see if that's correct. And for anybody not sure what to do, let's do it. Let's practice it. What color am I feeling? Let's pick a nice baby blue, light blue. I don't use this color enough, but it's kind of pretty. Okay, how many moles of chlorine are needed if okay, this question's worded really weird. It should just be, how many moles of chlorine would you need to make 2 moles of NCl3? That's a much easier way to say it. So how many moles of chlorine gas would you need to make 2 moles of NCl3? Nitrogen trichloride. Okay, so that means the chemical I'm looking for is chlorine. The chemical I'm given is NCl3, and it tells me it's 2 moles. You do not have to write this stuff down. Don't worry. This is just, me trying to, I guess, wrap my head around this before I get started. Okay, so I'm looking for moles of chlorine. So I take my 2 moles of NCl3 and I multiply it by my mole ratio. So I'm going to multiply it in this case by what is required. I'm looking for my moles of Cl2 and I'm dividing it by my moles that I'm given. If you're wondering where these numbers come from, I'll show you. Okay, hold on now. I'm going to be fancy here and pick a new color. So this 3 and this 2 come from my balanced chemical equation. Okay, this number comes from my question. That's a Q, not a very good looking Q. This number comes from, these numbers over here come from my equation. Okay, that's equation, sorry. There we go. Okay, so let's see. Now, I love this because I don't even need a calculator. 2 times 3 over 2 is certainly 3. I keep my significant figures, 3 moles. And then my answer is NCl3. Or sorry, Cl2. Cl2. I know it's Cl2 because These cancel. All right, we're going to do more of this. Don't worry. Well, I mean, between today and on Monday, we're going to do a lot of these because this is, again, this is the end of the chapter. Very, very important stuff. So this is a good question. This would be a great multiple choice question because it's very quick, but it's not really realistic, right? When you're in the lab, there's no device that measures moles. We don't use moles in the lab, like in the lab instructions or anything like that. Moles are something we calculate, not something we measure, not directly. What we measure in the lab is actually more like mass or volume. So how do we apply this to the lab, a lab situation? Well, these outcomes I'll do today. We're going to look at yield and mass calculations. This is a more realistic example. In an industrial process, maybe if any of my students here are pharmacy technicians, you might have to make up a certain amount of milligrams of ointment or milligrams of some medication. You need to know the recipe, and we don't use moles in a lab. We use grams. Like I said, the moles are converted after. So what we're going to do basically is take the subject we just did, like the topic we just did, and just expand on it a little, just a little. So in a lab, I'm going to give you an assignment. Imagine I'm paying you, you're my employee, you work at my company, and I say, hey, whoever, I want you to make 50 grams of copper. And I'll give you this equipment, I'll give you aluminum and copper 2 chloride, and I want you to use this formula, this recipe to make 50 grams of copper. We're going to need it. Well, anytime you're following a recipe and somebody asks you to make something, you need to figure out how many ingredients you have. Now, in this situation, I'm going to assume that the aluminum is the hardest part to make. So I'm going to ask ourselves, what mass of aluminum should we start with? I'm not going to worry about the amount of copper 2 chloride because that's an aqueous solution. And typically we have a lot of that, right? We would have hundreds of liters of aqueous solution in our lab that we could make at any time. The aluminum, however, that's a metal. How much do you need? How much metal will you have to buy or use to make 50 grams of copper? Well, there are 3 steps, and these 3 steps are always the same. Okay, always. I'm going to show you a practice problem here today with this. I'm going to show you 2. One is already completed, and then I'm going to do one with you. Okay, so how do we do it? Well, the mole ratio is called the mole ratio for a reason. We can only use the mole ratio with moles. I cannot use masses in my mole ratio. It's not called a mass ratio. It's not called a volume ratio. It's called a mole ratio. And I've told you guys this before. I've taught for so many years, like well over 10, well, not well over, but over 10 years, 11 or 12 years. And I've seen all sorts of types of these questions. Before I taught at the college, I taught in a high school system in Canada. We would do these questions all the time. And every year, every semester, every course, somebody would make the same mistake. They would use mass in a mole ratio calculation. You cannot do that. So step number 1 for this problem is, again, remember what I'm asking. I'm trying to find the amount of aluminum I need to make 50 grams of copper. So step number 1, find out how many moles of copper that is. We learned how to calculate moles in chapter 4. We basically only learned 3 equations for moles. You can have moles is mass over molar mass. You can have moles is particles over Avogadro's number. That we're not really ever going to see that again. Nobody in chemistry talks about particles in the lab. Another one we did is C times V. That's another good one. So we basically have two formulas that we can use in this type of question. Again, I'm never going to ask you about particles in a lab type situation. Nobody uses particles after first year chemistry. So step number one, find your moles. That would be mass over molar mass. Step number two, now that you've found moles, you can find the moles of aluminum using your recipe. It's a 3:2 ratio. Step number three, calculate the mass itself. You use the exact same formula. The only difference is, of course, you're using a different molar mass. So there's a little image here that kind of explains how this process works. I'm starting with the mass of copper. So step number one, I'm going to turn it into moles. Step number two, I'll use the mole ratio to come over here and find aluminum. And then step three, I'm going to answer the question. I'm going to calculate the mass. Again, nobody in a chemistry lab would say, hey, can you measure me 10 moles of aluminum? Like, no, we would use grams, 10 grams, 50 grams, 30 grams. So the calculations are already done here. Now, basically, I'll talk my way through these three steps, but then I'm going to do one with you. If you are confused right now with these three steps, just give me a minute because we will do slide 80 together. Okay, and then there's one more I'll get you guys to maybe practice next week. But anyways, so step number one, find the moles of copper. Well, moles of copper is the mass of copper divided by the molar mass. The molar mass, of course, is for copper. So 50 divided by the molar mass, I get 0.78 moles. We're only really using two significant figures. So now I can go to step two. Step two, now that I know the moles of copper, I can convert that to the moles of aluminum. So I take my mole ratio, this number, guys, let me highlight it. If any of you are wondering, where did 2/3 come from? It comes from my balanced chemical equation. I will show you this, don't worry. So the 2 and the 3 are from my balanced equation. It's 2 moles of aluminum for every 3 moles of copper. So I multiply it by 2/3, and I get my moles of aluminum. Now there's one step. The question is asking how much aluminum in grams. So I take my moles, I multiply it by my molar mass of aluminum, right? Make sure you use the molar mass of aluminum, and I get my answer, 14 grams. Very, very important, very, very challenging, or can be very challenging if you've never done this before. So guys, it's 4:06. We have lots of time, but I only need a few minutes. I want to show you one. I'm going to do this one for you. I will give you some to practice on Monday. We only have about 10 slides left for chapter 5. So we're getting very close to the end here of chapter 5. So let's look at this practice problem. Let me read it. I'll make a game plan. I'll make a strategy that we're going to do, and then we will solve it. What is the mass of sodium oxide, Na2O? It gives you the molar mass, which is great. Sorry. Because we don't have to calculate any molar masses in this question, not if they're given. So what is the mass of sodium oxide that will be produced from 15 grams of sodium carbonate? This is a decomposition reaction. Okay, let's make a plan. First things first, it's asking for the mass of this compound. So this compound, Na2O, this is our required, like this is what we're looking for. This chemical here, the sodium carbonate, this is what we're given. And we're given 15.00 grams of this. I'm ready to go. This is all of the information I need. I know the mass of my product, the mass of my reactant. Now I can find the mass of my product. So my steps are one, I'm going to find the moles of what I'm given. Step two, I'm going to use my mole ratio. so I can find my moles of my product. And step 3, once I find the moles of my product, I'm going to find the mass of my product. 3 steps. This would be worth maybe 3 marks, maybe 4 marks if you had to calculate your own molar masses. All right, let's pick a new color. Step number 1. Now, I do have to write a little small here, guys, because I didn't save myself much room. So step number 1, find the moles of Na2, CO3. So that's easy. It's mass over molar mass. So 15 grams over the molar mass. Luckily, the question gave you the molar mass. A lot of times, guys, in like chemistry 2, it's called chemistry 1121, but it's your second chemistry course. We give you the molar mass just to save time. In real life, molar masses would be written on the bottles of the chemicals. You could use Google. I mean, pretty straightforward. So I'm going to take my old trusty calculator. I'm using my phone, so hopefully it works. 15 divided by 61.9789. All right, so I get my answer. Oh, wait, I used the wrong molar mass, and I bet you there's somebody in the chat saying that. Yeah, Asil, thank you. I just realized that. Sorry, I used the wrong molar mass. This molar mass is for this chemical. This molar mass is for this chemical. Make sure you're using the same molar mass. So sorry about that. 105. I knew something didn't feel right. 9884. Okay, now I can do this. Sorry about that. That's pretty confusing, I know. But you make sure you use the correct molar mass, the molar mass for the element or chemical you're trying to find the moles for. So I can have 4 significant figures, so I end up getting 0.1415, and that's good enough for significant figures, but I'll put in 2 more just because we don't like to round our answer until the very end. All right, so that's step 1. Step 2, use your mole ratio. So I don't care about my moles of Na2CO3. I'm looking for moles of Na2O, the sodium oxide. So I'm going to find the moles of that using my balanced chemical equation, my recipe. So I take the answer that I just got, 141,525 moles of Na2CO3. You guys don't need to write all the things that I'm writing. This is just good for when you're studying. You can really kind of see where I'm going. Now, I multiply it by my mole ratio. I love this question because look at the balanced chemical equation. It's 1, 1, and 1. So really, you don't even need to do this step, but I like to show it just so we know, how the method works. Na2O divided by 1 mole of Na2CO3. Again, it seems really silly to do that because, we're literally just multiplying a number by 1, but it's nice to look at the procedure and, make sure everything is okay. So I get the same answer. This is totally normal for a chemical reaction, by the way. A lot of times the chemicals have a 1-to-1 ratio, meaning, 1 mole of this makes 1 mole of that. Okay, and the last part number 3. What color am I going to pick? Let's go dark blue. Okay, mass. The question is asking for mass. So my formula is moles times molar mass. So I take my number. This is why I didn't round it, by the way, because I want to keep a couple extra significant figures for the end. I'm multiplying it by my molar mass. That was given in the question, so my moles will cancel, and I'm left with the answer. Another cool thing, guys, about these questions or these problems is everything I'm doing, I'm leaving in my calculator. So I'm not actually clearing my calculator ever. So I take my answer from part 2 and I multiply it by the molar mass. 61.9789. And I get my answer. 4 significant figures, so 8.772 grams. I would need, I would make, if I took 15 grams of sodium carbonate, so I took 15 grams of sodium carbonate, I would end up with 8.772 grams of sodium oxide. And you might be thinking, well, whoa, hold up. The law of conservation of mass says that we can't create or destroy matter. So where did the other mass go? I'm going to ask you guys, and then I'm pretty much done, don't worry. Where did it go? Why isn't this equal to 15? Can anybody tell me where the other, 5.5 grams, where are they? 5.3 grams? Where did they go? Yeah, Tasneem, exactly. Yeah, exactly. Perfect. In the air. And Sarah, you're right too. They went in the air. They disappeared into the air as carbon dioxide. If you could do this in the lab, well, we could do this in the lab actually. We do this in chemistry 1200 actually. A way to do this is to heat it up. You just take sodium carbonate, that's basically baking soda, similar to baking soda, and you heat it up. Put it over a flame in a container, and it will decompose, and you'll notice that you lose mass. And technically, without any sources of error, if everything is accounted for, the mass of CO2 would exactly equal 15 when we added it to the 8.772. And again, that's if everything was perfect. We know not everything's perfect in real life. There's, you're going to lose some gas to the atmosphere, or it might not completely decompose, things like that. But yeah, that's it. This number, by the way, I'm done. I'm finished. Halas, 415 on a Thursday, that's enough. But this number that I just calculated is called the theoretical yield. And we'll talk more about this on Monday. We have, like I said, about 9 to 10 slides left for chapter 5. And then there is one more chapter, but don't be worried about that. It's only about 20 slides. It should only take maybe one class or less. But yeah, this number that I just got is called the theoretical yield. In a perfect world, that's what the chemicals I should get. And think about when you're baking. In a perfect world, your recipe might make 12 cookies, but you might only end up with 11. Maybe you ate some of the batter or dough or something. That happens to me all the time. I eat some of the cookie dough and then I don't get the proper amount of cookies. That's the theoretical yield is, in theory, if everything went perfect, that's what you'd get. But it's never perfect in real life, as you know. Whew. Okay, guys, I'm going to hit stop record. Your tests have been uploaded to D2L, so you guys can check your test marks. Test number 2, extremely very well marks. I mean, most people were getting 80s, and even more people were getting 100s or 90s. There was a lot of like 95, 97s, so very, very happy with your test. You can check your marks on D2L. The marks are not in SharePoint, they're not, or PeopleSoft, they're not there yet, but they will be. But for now, you can check your D2L, and I updated them today and a little bit last night, so you should see your marks. All right, I'm going to hit stop record. Any questions, let me know.